It's my pleasure to present you the first lecture by Professor Henrik Johansson from Uppsala University. And then he will be presenting to you guys some cool stuff about Color-Kinematics Duality and double copy. And in case you haven't heard those words, stay tuned for the next few days and you'll see a lot of stuff, cool stuff going on. So please, Henrik, you have any you want to.
All right, thank you, Gabriel. Yeah, it's a pleasure to be here in Brazil. First time here, also first time in South America. Although I'm a bit jet lagged and overwhelmed by the heat because I just came from 0 degrees Sweden. So just bear with me. If I wander off, let me know. So I will talk about essentially 2 closely related topics, which we usually refer to as color kinematics duality and double copy. And we already heard it being mentioned in David's lecture. He talked about how gravity can be thought of as square of Yang-Mills in certain cases. So that's basically double copy. And I will basically start today's lecture by saying a few words on double copy, but then I will quickly move into talking about color kinematics duality, because that's really the precursor for double copy. Once you understand color kinematics duality, then the double copy is actually not so hard to understand, even if that's the cooler part. So let's start. Just say some brief things about, well, maybe I do it over here since I already used half of the blackboard. So let's talk about the double copy a little bit. So essentially, one way to think of double copy is that it's just a statement that 1 plus 1 is equal to 2. Sometimes I like to write 1 times 1 is equal to 2, but that's of course not the correct equation. But that's essentially what we use. So what we use is that we have some states, and we like very much states which are spin 1. And what we do is that we tensor these spin 1 states. And then the result is going to be something which is spin 2. And that's what I meant by 1 plus 1 equals 2, which in terms of representation means that you multiply spin 1 representation and get spin 2. And that's, of course, something you learn very early in quantum mechanics. You can always tensor states to get higher spin. So that's not very exciting. That's kindergarten stuff. But what's exciting is that this generalized beyond states. So it also works for interactions. And this is precisely what we saw in David's talk, that if you have an amplitude, so now I'm just going to do it very schematically. So say you have 3 gluons, which I just denote by G, and then you multiply another amplitude by 3 gluon. It could be in Yang-Mills. Well, it should be in Yang-Mills, but here I'm just being very schematic. You basically get an amplitude of 3 gravitons, which I denote by the letter H. And that's cool, right? It's not just a level of the free spectrum. Also, for some of the simplest interactions or amplitudes, you can get a product rule where you multiply spin 1 objects and you get spin 2 objects. Yes? Yes, I will talk about, well, eventually I will talk about the full theory, which includes scalar and also antisymmetric tensor. But for now, I just talk about it in a very schematic way. In fact, this lecture will be a rather schematic, I would say, because there's some general properties where you don't even have to specify which theory you're talking about. So that's basically what's going to happen in this lecture to a large extent. And then, yeah, so as I say, this is cool because it works for interactions, but then you can sort of promote this idea to the next level. So the next level is that you just make it work for theories themselves, right? So you can make this statement that there's some product between Yang-Mills and Yang-Mills, basically itself, and this gives GR. And here, now let's come back to Ricardo's comment. There's some other stuff here. let me just say dot, dot, dot. So it's GR plus other stuff. And this is basically the slogan that you already heard in David's talk, that you can think of GR as some Yang-Mills squared. I think he only did it maybe at amplitude level, but that's basically the slogan you often hear, that GR is the square of Yang-Mills. And in this lecture, I'm going to make it slightly more precise by saying, well, it's really a multiplication rather than a squaring, and it's really going to be some extra stuff coming along for the ride. Okay, and the last thing I'm going to say about motivating the double copy is that you can also take it to maybe the next level, and that's talking about classical solutions. So people have looked at solutions in electromagnetism and then related them to solutions in GR. So for example, there's a relation between Coulomb solution. So basically 2 copies of Coulomb. And that has been matched to Schwarzschild, albeit in very special coordinates, which are basically called Kerr-Schild coordinates. Let's see if I can spell Schwarzschild correct. Maybe Ricardo can tell me if I did that. So the general idea here is that there's a lot of things you can take products between engaged theories, and they all seem to give sensible results in the gravity theory, and that's remarkable, because naively you would never imagine that could happen just by looking at the spectrum. Okay, and then another good thing here, or cool thing here, is that it sort of alludes to some new mathematical property of gravity that that you don't see in the Lagrangian. So let's put a check mark here and say it's a new mathematical property, which haven't been fully explored, I would say. So that means that lots of work remains. But it's not just a new structure, because there's lots of ways to formulate GR or gravity, and they all have their benefits and pros and cons. But here, one big pro is that it actually gives you computational efficiency. Sorry for my handwriting. I should say efficiency there. And that's one of the big, drawing points here, that it's not just about formulating something. Anybody can reformulate something and make it worse. The point is that it got better. And then, so I put check marks here, so let me put an X here. We don't understand it. We don't understand the double copy. The double copy. But that doesn't mean that we don't really have like a general framework where we can prove things mathematically, and when does it work, when does it not work, and statements like that. And that's why I put like it's a negative thing. It didn't pass. It got a cross instead of a check. But as a researcher, of course, it's a cool thing, right? Because it means that there's a lot of things to do. So especially if you're young and you're looking for a new project, trying to just understand the double copy better than we currently understand it. Okay, so that was the sales pitch for the double copy. And now I'm going to do a sales pitch for the Color-Kinematics Duality. So this is part 2, I guess. All right. So I think the number one sales pitch here is that if you have color kinematics duality under control, then the double copy is just a consequence of it, right? So the double copy is a derived property of color kinematics duality. In the sense that, you know, in order for us to take a gauge theory, and here I don't necessarily mean Young-Mills, it could be some other gauge theory. In order to do the double copy with this gauge theory, in order to get some gravity theory or something that is similar to gravity theory, you have to require certain properties of the gauge theory, and this is the property that there is some kind of duality or similarity between color and kinematics in these gauge theories, and also the other one in principle. If gauge theory satisfies color kinematics duality, you can plug it into this formula and you can do all the things that I had over there. And this essentially means that there's some similarity between the SUN, SUNC, color Lie algebra, and something that you can call maybe a kinematic Lie algebra. Which in many cases we don't know what it is, but there are some examples where we do know it. And the word duality here is maybe in a generalized sense. It just means that when we look at our Feynman diagrams, they have some structure. Let's just write it very schematically, that it has a color factor and it has a kinematic factor, and then it has some propagator. So that's roughly how our Feynman diagrams looks like in a gauge theory. And the statement is just saying that there is some kind of map between the color and the kinematic factors in our Feynman diagrams. And I'm being very schematic here because the rest of the lecture I will make it more precise. Okay. Yep. Yeah. Well, I mean, you can certainly take GR, or you can take GR plus various random matter, and that would be different gravity theories. You can also take higher derivative gravity theories. You can even write down theories which have different kind of kinetic terms than you're used to. Like you can do conformal gravity. That's completely different than GR, right? Yeah. Yeah. Well, so my claim here is that if you can prove, for example, color kinematics duality in a given theory, then you know that the double copy is just a derived property of color kinematics duality, right? Yeah. So, yeah, it seems like I'm still talking about double copy over here, but that's because, I mean, that's maybe the cool part, and I'm just saying that, you know, once you have understood this less cool thing, color kinematics duality, then you can do that. Yeah. No, I wouldn't say it's more general. I haven't really spelled out the details here. I'm just saying that, you know, let's try to understand color kinematics duality. Then some of the things that I said over there are going to follow from that, right? So I think there's no statements about more general. Anyhow, but it's a statement about gauge theory. Maybe that's why I have two different columns here. I'm talking about gauge theory here, and I'm talking about gravity over there, which I assume I'm going to take gauge theory and gravity to be different things. other people sometimes say gravity is a gauge theory, but that's a different statement. And so if you just think of color-kinematics duality by itself and ignore the double copy thing, it has a number of positive things about it. So it also implies a new mathematical structure. Yeah, I'm not. This chalk is not doing my handwriting any good. So it's a new mathematical structure. In gauge theory. It also leads to computational efficiency in gauge theory, never mind gravity. And it has actually the same downside, or X, that we don't understand it. We don't understand. And I will come to exactly what we don't understand. Well, I will say some of it today and maybe some of it in later lectures. Yep. Yep. So I'm referring to maybe this kinematic Lie algebra here. Yeah. I will talk about that a bit more later on. But other than that, it's just the fact that there is some some duality between these two factors in the amplitude or in the Feynman diagrams themselves, which is not obvious at all. It's not obvious from the Lagrangian. It's not obvious from previous formulations of gauge theories, Yang-Mills. Okay. So I'm still in the motivational part. Yeah, let's talk a bit more motivation. Why or what is color kinematics duality? So okay, this is still motivation, so it will be kind of schematic. What is color kinematics duality? And this is not the definition, so this is just some words. So first of all, it's an observed structure. No general proof. Sometimes you hear that certain things has been proven, but usually it just means that it has been constructed. It's just constructed proofs. Is present in most familiar gauge theories. Such as, Yang-Mills with matter, QCD, even more exotic ones like Chern-Simons and stuff like that. And as I said, it links color and kinematic degrees of freedom. So in some sense, you can think of color as being some internal space degrees of freedom, whereas kinematic is really your external or space-time degrees of freedom. And it's really hidden. It's hidden in standard QFT frameworks or formalism. And the reason why it's connected to amplitude is because amplitude is what actually exposed it. So it's exposed in on-shell scattering amplitudes. However, I should say that it's really something that wants to be off-shell, but it's hidden. But we will see later on that, however, it wants to be to live off-shell. And one way to see that is that I was talking about Feynman diagrams, and David said we should not talk about Feynman diagrams, so I'm already breaking David's rules here. And also, I should say here, there's a parenthesis here as well. So I said it's present in most gauge theories, but it also turns out to be present in some other theories. And some scalar EFTs. EFTs, effective field theories, which people are excited about, such as pions. Like when you scatter pions, it also seems to work there. All right. Okay, so I will slowly start to get more concrete. Okay, so now let's focus on color versus kinematics. And you already heard that being discussed in David's lectures. He was really focusing on the kinematic part, defining the variables and so on. And I think probably tomorrow's lecture he will probably talk about color, so I'm going to get a bit ahead of him. Let's take our random gauge theory, which might be QCD, for example, if you want, but it could just be pure Yang-Mills as well. And we're basically going to think of a gauge theory as having two parts. There's two parts that we're interested in. The SUNC, the gauge group, which is color. And then it's going to have some other structure, which is basically, so if this is the symmetry for color, the other symmetry is basically Poincare symmetry, right? And so generators for color, we typically just call them TA, so that's the generators of the Lie algebra. But we also have, of course, familiar other building blocks, which are structure constants, which was mentioned in David's lecture. But if you think about Poincare symmetry, then we need to think about what are the generators. Well, it's the momenta, and it's the Lorentz rotations, Lorentz symmetry. And then when we build up amplitudes, we build up things which are invariant under the symmetries. So for example, we write particles as having definite momenta. This is supposed to be a little p. Or as we heard in David's lecture, we also use, we think about the rotations, and then we think about the little group. Which leaves the momenta invariant, and then we obtain our polarizations, which are functions of momenta, or we obtain our spinors that David introduced. Let's just write the lambda p. I guess there was an alpha as well. Oh, let's write the other one as well. So David, in his lecture today, he introduced the lambdas essentially as efficient ways to express the momenta, and the polarizations, but the lambdas themselves are also they're also on-shell polarizations for the spinners. So if you have fermions in your theory, then you would have separate lambdas for them as well. I guess I didn't say that, but that's the intended meaning here. I'm not saying that you have epsilon p and lambda tilde. That would be redundant. I'm saying you could also have fermions in your theory, right? Okay, so then, having talked about the building blocks, we can now schematically think about the amplitude as being some kind of sum over ingredients which have both color and kinematic factors. So generally, I'm just going to denote it like this, and I will be more precise later on. But you have some sum over terms. These terms have a color factor built out of these ingredients. It has some what we call typically partial amplitude built out of these ingredients. So we have the color factor. Ci. So Ci is a function. It's a function of, well, which graph you're thinking of or whatever, or which decomposition you're thinking of, but also of the generators. And I put this curly bracket here to just denote that you have many of them, depending on which particles you're talking about and so on. That's your color factor. And then you have some partial amplitude. Which in the general meaning, you can just define to be the coefficient in front of each color factor, or vice versa, the color factor is the coefficient in front of the partial amplitude. So AI is a function of your momenta, your polarization, and lambda, lambda twiddle. You can also work with felicities, as David did. Here, I'm just thinking about doing it in general dimensions, so I don't want to commit to certain felicities. Yes? Sorry, can you say a bit louder? No, there's no direct relation between the color and the kinematic. It's rather that they are correlated in the sense that, you know, if you have certain properties that the color factor satisfies, then those properties also needs to be satisfied in the kinematic part, but they're not the same properties, they're just very similar properties. I mean, yeah, so it's, or yeah, maybe I get what you're asking. So if you're changing in color, do you get a different kinematic algebra? Yeah, to a certain extent. So, for example, if you don't allow like fundamental representation, that's like a constraint on your color structure, then that might have some implication on the kinematic part and so on. But it's more indirect. I would say it's less direct dependence and more indirect, you know. Yes, so if you have supersymmetry, I would definitely say that that has to do with the kinematic part, because then you know that the Poincare group lifts to a higher extended supergroup, right? So that will definitely go into the Poincare algebra, and it would definitely go into the partial amplitudes. Yeah, so when you have supersymmetry, nothing changes about your color factor, right? They stay the same. Yeah, you can also ask about flavor. Let's say if you have some flavor symmetry, that's of course another symmetry, and where would you put it? Sometimes you put it with the kinematic part, or you can also bake it into the color part. You can basically say that flavor came from spontaneously breaking some bigger gauge group or something like that. Or you can keep it as a separate third ingredient here. anyway works. But essentially, the general strategy here is that we're going to identify color factors and then kinematic factors, and then we're going to keep them separate. You know, they live their own life. So this is only color. And this is only kinematics. Okay, and then I should say that all the hard part about computing amplitudes is to figure out these partial amplitudes, because figuring out what color factors are is trivial, right? They just multiply generators and structure constants together, and then you can fit it into some computer algebra or whatever to work out what they evaluate to when you sum over all the indices and whatever. But it's kind of it's not very profound. It's easily done by hand or by computer. So all the hard part is actually in trying to figure out what is this kinematic partial amplitudes. And yeah, so as I said, the SUNC color factors are trivial. Well, they're maybe not trivial if it's the first time you've seen them, but once you get used to them, they become trivial fairly soon. So that means that we're not going to talk about them too much. We are going to talk about them a little bit, but not too much. But yeah, it's really here in the Poincare. Maybe I should say there's of course a lot of other stuff here that you need to worry about in the kinematic part. So for example, you need to worry about Poincare. You need to worry about gauge symmetry. And here, okay, you might be confused because wasn't that the gauge group? What I really mean here is maybe linearized gauge symmetry at the level of the amplitude, because that's basically just something that you do at the level of your kinematic building blocks. You don't actually touch the color when you do linearized gauge symmetry. You need to worry about locality. Locality is essentially where are your poles located and how do they, well, where are your poles located? Are they just standard Feynman propagators and so on? Then you need to worry about the residues, which has to do with unitarity. And some of these words you already seen, but all of those ingredients goes into constructing your partial amplitude, and that's non-trivial. And here I'm taking the same philosophy as in David's talk, that you don't just, you don't crank out your Feynman rules from the Lagrangian and do your Feynman calculations that way. You try to be a bit smarter about it, because if you're smarter about it, you can actually improve your computational efficiency. But that means that you need to consider all of these things separately and not as being output of your Feynman rules, but rather being constraints that you need to make sure are satisfied. Okay? Any other questions? All right, so yes, I think I was going to talk about color factors now. So yeah, I should warn you that this is very basic lecture today, and it will maybe get more exciting tomorrow. But let's talk about color, which I already declared to be trivial. Okay, so color factors. So I'm not going to do it the formal or textbook way, of course. I'm just going to do what is needed. What do we need to know in order to do amplitude calculations? Well, so in the simplest case where you have fundamental and adjoint, that means that you can now build your color factors from generators, TA, and structure constants. FABC. And of course, you know the usual relation, which is the defining relation for a Lie algebra. And I should make a comment here that often we don't use this structure constant in amplitude. Sometimes we use slightly different one. So the one that I actually like to use is F twiddle, which, well, the main difference between the usual structure constant and this one is that it's actually imaginary. So I just put an I here. Basically, I'm absorbing the I that I wrote here. So this is basically F twiddle. I think some authors also put some square root of 2 factors because they don't like certain square root of 2 factors that appear in the amplitude. But here I'm just going to say that the difference between F and F tilde is just an I. And by the way, that's also what the mathematicians do for some. Sometimes mathematicians actually do not like the I, so they just work with imaginary sort constants. It makes the reality properties a bit harder to see, but it has the benefit that you don't have to think about, oh, does my color factor include an I or not an I, right? Because now everything is uniform in I's. Okay, so with this FABC twiddle, you can actually just solve this equation and write your structure constant in terms of the generators themselves. So you can write it as a trace of TA, TB, and then TC product. And what we're using here is that the trace of 2 generators, you can always normalize to whatever you want. So I take it to be delta AB. David will probably talk about this tomorrow, and I hope he doesn't pick 2 different conventions for me. And then one very important identity that you need to keep track of is the Jacobi identity. And that's just the fact that if you sew together or you multiply 2 FABCs, and now it doesn't matter whether they're tilde or not because it's homogeneous, C, D, E, and then you add the cyclic permutation, or maybe let me just change it a bit here. So let's put the E, and C, D. So now you just add cyclic permutation of I guess any 3 free indices here, so that would be like A, B, C. Just add the cyclic completion. This is equal to 0. That's the Jacobi identity. And this one can be represented diagrammatically. So this is going to be quite useful for later purposes. But you can think of this as 2 3-point vertices that you have sewn together. So this diagram would be this guy, where I have A, B, C, D, and the internal one is E, but that one we can ignore. And then I'm just saying if you add the same diagram, but you have cyclically permuted ABC. So should I do it? Okay. Well, I guess what people usually do is that they do it in some diagrammatic way, which I'm not going to do very well. Let me just do it. Same diagram 3 times. So what did I say? So B, C, A. Let's keep D at the same location. And then C, A, B. So the sum of these three diagrams is 0. Now, why is that important? Well, it's important because when you write down your amplitude, you're going to write some color factors. No matter how you do your calculation, you're going to write down some color factors. And you have to be careful to not write down an overcomplete basis of them, because then their coefficients might not necessarily be gauge invariant. So often what you want to do is that you want to basically write down your amplitude, and then you want to mod out by such relations such that you land in a true basis of color factors. But actually, let me draw that identity slightly prettier. Actually, I don't have it in my notes, so let's see if I can remember how I usually draw it. Yes, I think I draw it like this. Minus that's a slightly prettier way of doing it. And now all the legs are in the same location. Whoopsie. Okay. So that's also the Jacobi. Okay. And now, as I just said, that typically when you do a calculation, you end up with a long list of color factors. Like you have color factor 1, this is a bunch of Fs. Let me not write any indices, but basically a long string of Fs. Then you do your color factor 2, there's also a long string of Fs, and so on, right? And then you have a bunch of color factors. And typically, if you're in the case that you only have adjoint particles and that you're at endpoints, it turns out that there's a known number how many color factors you have, and that's 2n minus 5 double factorial. These are basically all the color factors you can construct at endpoints. So this is endpoint 3 amplitude with only adjoint. Particles. And I didn't say anything about what theory this is or which gauge group it is or whatever. Is it supersymmetric? I don't care. I'm just saying that if you just list all of your cubic diagrams that you can construct out of contracting FABCs, you get exactly 2n minus 5 factorial. Yeah. Here? There's many ways to contract the Fs. You can also construct the Fs so that you get loops, but here I just mean that you're doing tree level. So just contract them in many different ways. And my claim is that you can only get that many. You can only get 2n minus 5 double factorial number of contractions. And the reason why you can only get that is because that's essentially the number of cubic diagrams at endpoints. So I guess I want to try to explain that. Okay. So let's study the number of cubic diagrams. And I don't mean Feynman diagrams here. I just mean stuff that you can get from multiplying together FABCs. I still call them diagrams. So obviously, we're going to start at 3 points. N equals 3. This is what David also did. He started with 3-point scattering. So there's basically only one diagram I can draw. Let me not put what the legs are. I mean, it could be 1, 2, 3, or whatever, or A, B, C, but there's only one. So one diagram. Then I think most of you probably know that when I get to 4-point, there's 3 diagrams, which I'm not going to draw. But basically, you know, STU channel, you know it, there's 3 of them. So this is n equals 4. Then you get to n equals 5. Let me just draw one diagram. And my claim is that all other diagrams are permutations of this guy, basically by putting the labels in different ways. Does anybody know how many there are? What's the next number? 1, 3. What did you say? 15, yes. So that can be written as 3 times 5, 15. And then, of course, when you get to 6-point, you can actually draw 2 different, what people call topologies, which maybe mathematicians would not agree are topologies, but we call it that. So you can draw these types of diagrams. And here you can also you can find out that the number here is actually 3 times 5 times 7, which I guess is what? 7 times 15. I don't remember. I cannot. What? 105. Good, thanks. When you say it, I remembered it. And then you can, of course, complete this. And my claim is that if you complete it, you get 2n minus 5 double factorial, which I guess you can see is what the pattern gives. But of course, I just cooked up the pattern from nowhere. But this is actually my first homework done. So homework, construct proof, like mathematical proof. Of the fact that that's the number of cubic diagrams. Once you figure out how to do it, it's actually not hard. But before you figure out, this can be quite hard. All right, so why am I talking about this? Well, as I said before, you get that many diagrams or color factors, but they're not independent. So you have to do something about that, right? Because it's too many. So now comes the task of using the Jacobi relation to try to reduce the number of independent color factors. And people have figured out that there is one way to do it at tree level, which always works. At loop level, I don't think people have figured out how to do it yet. But essentially, you can draw this, what some people call half-ladder diagrams, because it kind of looks like somebody took a ladder and cut it in half. I guess it looks even more like a ladder if I do this. So that's a half-ladder diagram. And then you say, well, if you have a half-ladder diagram, then you're fine. You just leave it as it is. But what happens if you have like a branch sticking out from one of these half-ladders? Well, then you just use Jacobi. You use the Jacobi to remove it. So the Jacobi relation is now what I wrote over there, that you just write it now. I guess I should have used a different color. So let's make it yellow. So you basically keep most of the diagrams the same, and I'm not even sure I have the same number of legs here. Like something like that. And then you basically just move it down such that now it touches the whatever I don't know what's called, the leg of the ladder. And then you subtract the permuted one. So 1, 2, 3, 4, 1, 2, 3, 4. So there's a permuted one, which is basically this one, or non-planar one. right? All right, so the claim is that that's a Jacobi. You see a branch sticking out, then you reduce it such that it becomes two half ladders. This was not a half ladder, but now it's half ladders, and you're done. I hope you can see that it's the same relation. Maybe it's just permuted. It's rotated in some way. Yeah, it's easiest if you think of this diagram as being that, and then you think of this diagram as being that, and so on. Okay, and if you have more branches sticking out, well, then you just repeat it. And also that works if you have branches on branches. Or forks, I guess people call them forks as well. So the thing is that you can always reduce this to this half ladder. And that's as well, that's the same. All right. So now this actually takes me to the second homework. So if this is homework 1, this is homework 2. So homework 2 is that you should draw all these 15 diagrams, and then try to figure out that using some reduction along these lines, you can figure out how many Jacobis there are. Or let me phrase it more. So the homework is draw all diagrams. Draw all color diagrams at 5 points. Count how many Jacobis there are, how many Jacobi entities there are. Are present. That relates this 15. And then the next question is, are they all independent? And here I mean the Jacobis, right? Are the Jacobi identities independent? So basically what I need for you is the number, how many Jacobi identities are there, and are they all independent equations? Yes or no? And we can do the same exercise of 4-point. So there's 3 diagrams, and there's 1 Jacobi identity. Clearly it's independent. There's only one. Okay, so now I basically motivated the existence of these half-ladder diagrams. Okay, so let's talk about the half-ladder. Basis of color factors. Okay. So essentially we can, if I draw the half-ladder again, what we can always make, which wasn't very clear maybe here, but you always make the first and the last particle the same. So let's pick the first leg to be particle 1 and the last leg to be particle n. But then you can, for this rungs that sticks out of the half ladder, they can be any particle. So you basically need to denote it by permutation. So I'm going to use the letter sigma for permutation. So this is basically permutation entry 2, permutation entry 3, permutation entry 4, and then sigma n minus 2. Oof, doesn't fit. Sigma n minus 2. Sigma n minus 1. So sigma is a permutation of n minus 2 elements. Okay, I guess I reserved sigma 1 to always be equal to 1, and sigma n is always equal to n. And then, okay, now I can write out the explicit color factor, so it's A1, A sigma 2, B, FB, A sigma 3, C, dot, 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 F. Let's use the letter Y, even though that's a limited number of letters, I guess. A n minus 2, sorry, sigma n minus 2, Z, F, Z, A sigma n minus 1, and then A n. Okay, so that's my whole color factor now. So I can write that color factor and all its permutation on one line. And often we just give it a very generic name. We just call it C1, sigma 2, sigma 3, sigma 4, sigma n minus 2, sigma n minus 1, sigma, or if you, n. Or if you wish, you can just call it C1, sigma, and n. So that's basically, now the sigma is just a string of numbers. And so this sigma here, sigma is a permutation of the group Sn minus 2, the permutation group, basically. Okay. Okay, so that kind of answers the question of how many color factors are there really. So there's not actually 2n minus 5 double factorial because they're related, but there are as many as there are permutations, right? In this permutation group. So there are precisely n minus 2 factorial terms, color factors, independent color factors. At endpoints and tree level. If you ask the same question at L loops, then I don't know if there's an answer to that question, how many there are. You have to work it out. Okay, so this means that now we can write down a formula for our amplitude in terms of these color factors. So people typically write this curly amplitude AN. So in this case, it's a tree-level amplitude, but it's a tree-level amplitude at endpoint, and it's a sum. It's a sum of permutations belonging to this permutation group, Sn minus 2, and it has the color factor, the half-ladder color factor, 1 sigma n, and then it has a partial amplitude where we can now recycle the notation. So we just write 1 sigma n, because it also depends on the same permutation. And this formula is known as the DDM formula. So it's Dixon, Del Duca, Maltoni. And I think the reason why he has the name is because when they first formulated it, it was quite a surprise that it existed. Well, what's surprising is that these coefficients here are very special. So these coefficients here, A1 sigma n, are known as color-ordered, color-ordered partial amplitudes. And I think we're going to see, David is probably going to talk about this, or he has already started talking about them, but he hasn't maybe defined them in a most general sense. But they're actually usually not defined, they're not defined in this DDM basis, but they're usually defined in a trace basis, which I'm not going to talk about because that probably belongs to David's talk, the lectures. But if you know anything about the trace basis, this is the same amplitudes as in trace decomposition of tracing of full amplitude. But here's just a parenthesis. Okay, so yeah, so you can already see here that there are some similarities between our color and kinematics. But now let's talk about what are the actual properties of our kinematic amplitude. And I'm doing this discussion very generally because this applies to Yang-Mills. It also applies to a bunch of other gauge series. So let's talk about partial amplitudes. So the most important fact about partial amplitudes is that they're gauge invariant. So A, 1, comma, sigma, comma, n is gauge invariant. And they're gauge invariant functions of the kinematic building blocks. So P mu I, epsilon mu I if you have polarizations, lambda I, lambda twiddle alpha dot I if you have spinors, or if you have eliminated your P and epsilon, you can also write it in terms of just lambdas. Here I is the number of particles. Or sorry, I labels the particles. Okay, so why is it gauge invariant? Well, it's gauge invariant because what I just did, I took the full amplitude, which is supposed to be gauge invariant, and then I decomposed it in a basis, like a true basis of n minus 2 independent color factors. Since it's in a basis, that means that every element that multiplies those basis color factor has to be gauge invariant. Okay, so what's not so obvious here, but is obvious maybe in the usual trace decomposition, is that these amplitudes are actually planar amplitudes. They're planar and they're cyclically invariant. That means that I can do a cyclic permutation, 1, 2, 3, n. Sometimes I write commas, sometimes I don't write commas. It's a bit random, I guess. 2, 3, n, and 1. So I can just do a cyclic permutation and amplitude stays the same. And you note that that's a permutation which I didn't actually allow here, right? So that's actually like, it goes outside of this sum. But you can write down those amplitudes, and they're actually the same by cyclic symmetry. And planar here means that I'm only allowed to draw Feynman diagrams that that I can draw on a plane. These are the only ones that contribute. That also means that I'm only allowed to have poles in consecutive particle momenta. So basically Mandelstoms where the momenta is added up consecutively. I'm not going to try to motivate why they're planar. It's not at all obvious from what I just did. That's kind of part of the miracle. Another symmetry that they have is that they have reversal symmetry. That means that if I take the reversed order, so if I start with n, and then I go down to n minus 1, whatever, n minus 2, 2 and 1, that's the same thing as writing the normal order, 1, 2, 3, up to n minus 1 and up to a minus sign. So the minus sign depends on how many particles you have. So if I have odd number of particles, that's a minus sign. And this reflection symmetry, I think, is fairly easy to see from this formula, because the color factor actually has the same reflection symmetry. If you just look at the color factor, if I wrote it in the reversed order, it would be the same up to a minus sign. And since the full amplitude has to be fully Bose symmetric, it follows that this has to have that reflection symmetry. Yeah. Yeah, I'm still stuck at 3 level. Yes, I will. Yeah, so I drew a non-planar diagram before. I drew this diagram. I call that non-planar, just based on how I drew it, right? So 1, 2, 3, 4. Of course, everything is planar up to a permutation, but if I don't allow permutations, I would call it non-planar. And it's still a useful characterization because it tells you which diagrams are allowed and which ones are not allowed, right? Yeah. Okay. Okay. Then another interesting property that these amplitudes have is known as U1 decoupling. U1 decoupling identity. And now it sounds like I'm talking about, you know, QCD and photons and whatever, but I'm not talking about that. I'm just saying this is a property of color factors alone, but it imposes a relation on the partial amplitudes. So the statement is that if you have a U1 photon as part of your gauge group, let's say you have like SU NC times U1, and that's your gauge group. Then the claim is that if that's true, then your amplitude has to vanish if one of the external particles is a photon. So that has to be true because photons don't couple to gluons, but it's really a statement that these Fs are actually 0. Like if I actually plug in a photon, well, the Fs just vanish because F is non-abelian. But it has a consequence for the partial amplitude, which is highly non-trivial, and that's if you sum. I don't know if that's what happened to my yellow one there. Okay, so if you take one particle, which we can call a photon, let's take it to be particle 1, and then you have the rest, which are non-abelian. And then you add the amplitude where you move this particle around, like to the second slot. And then you keep moving it. Okay, I'm going to run out of space. 2, 3, 1. Plus, okay, so plus dot 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 a 2, 3, 1 and minus 1 and okay, I guess one more. Okay. that's a 1, and n. And I don't need to move it to the last slot, because by cyclicity, that's the same as this guy. But if you add up all of these guys, this is actually 0. 0 is equal to this thing. And physically, what it means is that since particle 1, which is my photon, or U1 particle, it doesn't have a color, so it means that it should be inserted at every possible place in the amplitude, whereas you keep the ordering of the other particles fixed because they are non-abelian. So you have to insert it in every possible location, which basically means n locations. And the sum has to be 0. And that's a non-trivial identity, which you can derive purely based on the color factors, even though I didn't specify at all what the functions A are. But it turns out that this U1 decoupling identity, or photon decoupling identity, this is just one identity in a big family of identities. And that big family of identities is called Kleist-Coif identities, after the authors who came up with them, or Kleist-Coif relations. And okay, let's see if I can try to write it below here, maybe. So if you take an amplitude where you put like 1 first, then you put some alpha, which is now a set. Let me underscore it to mean that it's a set. Then we have particle n, and then we have another set beta. Let me underscore it. So let's say we have an amplitude of this form. It turns out that you can always move leg n to the very end. So you can move it past all this beta set. And there's a formula for that, which is the following. So minus n, and then to the power of how many beta elements is. So I'm going to denote that by basically absolute of beta, that's the number of elements. Then it's a sum of permutation sigma. Let me write that shortly, but it's basically in the basis element, in the basis now. So it's in this DDM basis where we have sigma in the middle and n at the end. But then what is this sigma? So sigma here, which is also a set, of course, is alpha shuffle product with beta transpose. So beta transpose is just take beta but reverse the order. And shuffle product, which is using this Russian character, it just means that you shuffle it like a deck of cards, like all possible shuffling between alpha and beta. I'm not going to try to explain what it is other than that, but you can look up. It's a well-known product, shuffle product. And this identity here, this means that you can always put it in this basis, which is precisely the basis up here, right? And you could have said, well, I mean, we started from that basis, so why do you have to argue that you can always move back to the basis? Well, the point is that I can do any permutation here. I can permute over the whole cyclic group, or the whole permutation group, sigma n. And with the Kleist-Coif, I can always go back to this basis, right? So it's a true basis, right? So the conclusion here is that the basis of partial amplitudes is same as color basis. And that's it's a non-trivial statement, even though it sounds like we almost kind of derived it over here, but we didn't. You need all of this Kleist-Coif machinery, U1 decoupling, and so on, cyclic symmetry. All of that needs to be in place in order for you to declare that the basis is truly n minus 2 factorial. Did I say that? n minus 2. n minus 2 factorial. yeah, sorry, single factorial, not a double factorial. Okay. Okay. How am I doing on time? Yes. Yes. That's the size of the basis, and now of course, you can pick any basis, meaning that you can pick any two legs, and you can keep them fixed in your basis because all of those bases are equivalent bases. But the size of the size of the linear space that this partial amplitude lives in is n minus 2 factorial. Yeah, both for the color and for the kinematics. And those two statements are independent. I mean, there are two different statements. They're not, one is not following from the other. So it's a non-trivial thing. So you said 15 minutes? Yeah. Okay, yeah. Good. Yes. Okay, so I just introduced these Kleist relations ad hoc. And I didn't even motivate why they exist. I'm motivated why the U1 decoupling exists. But what's the meaning of these Kleist relations? And I think for a long time it was kind of a mystery what they are. But it turned out that, I mean, you can actually show that they follow from some very simple considerations. And by follow, I don't mean, I'm not going to present a proof, but I'm just going to present like an observation. So let's try. Let's make this KK. So sometimes people call it KK, not to be confused with Klein, which is also called KK. Let's try to make the manifest. And so by manifest, I mean we're going to write our partial amplitude in such a way that they no longer are needed. So let's write our amplitude 1 sigma n as a sum over planar graphs. Planar cubic graphs. And I'm just going to denote that with, well, let's say I belongs to the set of planar cubic graphs. So we have some numerator, and we have some denominator for each graph. And on top of it, we might have a sign. The sign is a bit ambiguous, so I'm just going to denote it by -1 to the power of the permutation. Sorry, permutation? Well, I guess in my notes I wrote something like that. I don't know, maybe I don't know what to write here. There's a sign ambiguity because you can always redefine your graphs with a minus sign, so there's some ambiguity here. Let me not be very precise about what this is. Okay, so what are these building blocks now? Well, as I said, they're planar cubic graphs. This is just, we know that all Feynman graphs basically have a denominator and a numerator. The denominator basically encodes the pole structures. The numerator encodes the tensor structure that you have in gauge theories. So that's what this notation means. Yes, and what is this index I here? Well, this is basically just a list of all cubic graphs. So all cubic are given by some list. So 1, 2, up to n minus 5 double factorial. So that's the same number as before, which is no surprise because before we just used these graphs to denote color factors. Now I'm going to use the same graphs to denote kinematic objects. So this is a fully kinematic object. and there's n minus 5 double factorial of those objects. You might object and say that if you do a gauge theory like Yang-Mills, you also have contact diagrams, you have quartic vertices, but I'm going to ignore, for this discussion, I'm just going to ignore those vertices, and I'm going to say that they're not really needed, they add nothing to the discussion, and later on I'm going to say that you can just remove them by simply absorbing them into these diagrams. Okay, so that's all the cubic graphs, so that's basically all our building blocks. But then, sorry. Okay, this is what I meant to write here. So there's some sign here, which depends on the permutation, maybe. Well, okay. Yes. Anyhow, I'm being a bit schematic here, but the point is that we have all cubic graphs, and then we need to basically decide which of them are planar with respect to this ordering sigma here, right? And let me just say how many planar graphs there are in a given ordering. So in a given ordering, you only allow a certain subset of these graphs to exist, and basically that subset goes from 1 up to the Catalan number. So this is the Catalan number. Which has a formula. So let me Cn, so this is separate. Cn equals to 1 over k. I don't have space. Let me do it here. Ck 1 over k plus 1, and then it's just binomial numbers. So 2k over k. That's the Catalan number. Okay, I'm getting a bit schematic here. I was blaming it on my jet lag. Let's try to explain what I'm doing here. So di are denominators of cubic Feynman graphs. So David, in his lecture, made a distinction between diagram and integral. Unfortunately, since I'm doing tree level, I can't use the word integral, so let me use graph instead. This is like a generic word, which basically means the same thing as what David used, but he used the word integral. Graphs. And basically, their purpose is to capture all poles of the propagator. Okay, and then the Ni here are my numerators, or kinematic numerators. Okay, so the di are just function of momenta. So let's just write it like this. They're a function of the momenta p of your diagram, and the numerator are functions of the rest. So basically, p itself, it can also be in the numerator, and then the polarization. And if you have spinors, it can also be a function of spinors. And it captures all the non-trivial. So let's write here, captures all non-trivial. kinematic dependence of graph, of diagram. Maybe diagram is better. Right, so basically what I'm saying here is that you can, for a given graph, you can trivialize the denominators because you know what they are very easily, but the numerator is much trickier to compute. And okay, so what is this sketchy notation here that I couldn't decide what it was? What is -1 to the sigma? It denotes a permutation dependent sign. So for example, let me write the numerator for this graph, 1, 2, 3. So I'm just going to do it very schematically. The numerator is a function of that graph. This is what this notation means. And then the claim is that if I write down this graph, where I have permuted 1 and 2, so basically this is the same graph as that one, but I have permuted 1 and 2, which I did by folding the graph on top of itself, then this numerator is minus that numerator, right? So that's basically, depending on how you draw your graphs, that could be a sign. So I would say this is a planar graph, this is a non-planar one, but they're related, of course, with a minus sign. And this is important because for the color factor, it works exactly the same way. So if I have my color factors and I have this graph, then you know that this is F A1, A2, A3, and then this is, of course, minus this graph, which is equal to minus F. And now I guess should put it in different ordering, A2, A1, A3, right? So I'm just trying to now make the symmetry properties of color graphs, trying to impose them on numerator graphs. Even though we haven't specified what these numerators are, I'm just trying to now say they have to be the same. Okay, so the claim is now that if you write down your partial amplitudes as a sum over planar cubic graphs in some ordering sigma, put the appropriate signs such that they have the same signs as the color factors, then that makes Kleist-Coiffer relations manifest. So that's my claim. So KK is now manifest. Also planarity. And cyclicity is manifest. And furthermore, our poles are manifest because we have introduced them here. Poles are manifest. Also reversal symmetry and U1 decoupling. Or although you can think of reversal symmetry and U1 decoupling as being part of the Kleist-Coiffer relations, they're actually not independent. Okay, so that's just a claim, and let me now show you in one example that it works out. So I'm just going to show the very simplest example. But you can show it more generally, case by case. I don't know if there's a proof of it, but so, for example, let's take the 4-point case. I have 4 particles. Let's call them 1, 2, 3, 4. And as I said here, you have to now write down. You have to write down a sum of graphs in a certain ordering. So basically, it's going to be this graph and that graph in the 1, 2, 3, 4, 1, 2, 3, 4 ordering. They're both planar. Now, usually when we draw a graph, we mean that the graph includes everything. It includes color factor, kinematics, and poles. But here I want to make a distinction. So let's make a distinction between the numerator of that graph, and then we're just going to divide by the denominator, which is s. And then we're just going to add, well, numerator. Actually, I don't need an I here. I don't know why I have an N. So the numerator of that graph over t. And I made a mistake here, so I want to put the minus sign here, minus. Okay. And then you can write down another ordering. So as I said, well, I don't know if I said it, but I think I didn't. But there are basically three different orderings that you can consider. So here's one ordering. Okay. Minus n. Let's see, the same graphs. Same graph over s. And here you have plus n, and here you have a non-planar graph. So I draw it as a planar graph, but it's really planar in this ordering. And this ordering is planar, but since I like to draw it in a one canonical ordering, it looks non-planar. Okay, and then finally, there's one more permutation. 1, 4, 2, 3. There are some other permutations you can draw, but they are basically the same, which you convince yourself very easily. So the numerator of this graph over t, and then minus the numerator of this planar, non-planar graph over u. So STU are the Mandelstams. STU S is equal to whatever P1 plus P2 squared. T is P2 plus P3 squared. U is P1 plus P2 squared. And since we're doing massless scattering here, this is we have the identity S plus T plus U is equal to 0. But my point is that these are basically the 3 permutations which looks distinct, but now you can just add them together, and the whole answer become 0. And that's obvious. You can see it's obvious 0 because for every graph appears twice, and it always appears with minus sign. This graph appears here, here. This is a plus sign. I guess it's not so obvious. This graph here, here. So it always appears pairwise with opposite signs. And so that my claim is that this is the U1 decoupling. This here is the U1 decoupling identity at 4-point, which is the simplest KK Kleist-Coif relation. It's the only Kleist-Coif relation at 4-point. And it just follows from this sign. And this sign is just mimicking the sign of the color factors, but now applied to the kinematic graphs instead. Okay, and I'm probably out of time, yes. But maybe I should summarize what I said here. So I'm basically just slowly working my way in the direction of trying to make the kinematics behave as color. I don't know if you noticed that that's what I was doing. And you see that by doing that, I get more properties being manifest. I get like this cryptic KK relation is now manifest. Planarity is manifest. Cyclicity. Poles are manifest. That's very important, especially when you do loops. You always want to have your poles manifest. and so on. So we're making some progress here in trying to understand what is the kinematic dependence and ingredients of a gauge theory amplitude. And we have done all of those things without actually saying which theory we're talking about. I mean, of course, you can think of this as being pure Yang-Mills or pure QCD or whatever, or supersymmetric QCD, but it applies to all of them. And that's basically what I want to say today. So thanks.
Okay, guys, so we have time for one quick question before the coffee and then further on the discussion section.
Sorry, can you apply this to our symmetry? Because it doesn't commute with
Sorry,
our symmetry?
Our symmetry?
Yeah.
Well, our symmetry I would just absorb into my numerators because that's really kinematic symmetry. I mean, it's really part of the supersymmetry algebra, and you know, it lifts a supergroup, I guess. Yeah. So I wouldn't. Yes, at this point, everything I said holds, whether or not you have supersymmetry or not. You know, whether you have R symmetry or not, right? It's kind of irrelevant. So all I did here is I split color from the rest, so you can put everything, the rest, in the kinematic building blocks, right? Yeah.
But you can have color factors in our symmetry, right?
Hmm?
You can have color factors in our symmetry.
Yes. But what I'm saying here is that whether or not you have R symmetry plays no role for the color factors. Yeah.
Okay, guys, so let's move on to the coffee break and then we get back to the discussion sections.
Yeah, when you come back, you remember if you have a sparkler for your poster, we show after the coffee break.
Okay, see you.